All right, so today we are going to discuss about protection and deprotection of diols. So what is a diol? So we have two type of diols. We have a geminal diol and we have a vicinal diol. In a geminal diol, you will have two OH groups attached to same carbon. In a vicinal diol, you will have two OH groups at 1,2 position. Right? Now the geminal diol can be written as, so you have two OH groups attached to same carbon atom. And the vicinal diol can be represented as, so we have two OH groups at 1,2 position. Basically they are neighbors to each other. Now we generally do not protect geminal diols, but we do protect vicinal diols. So what is the reason why we don't protect geminal diol? The reason is when you have two OH groups at same carbon, by eliminating water, they are able to form aldehyde or ketone. So that is the primary reason why we don't protect geminal diol, but we do protect vicinal diols. So now let's move forward and look out what are the strategies available to protect vicinal diols. Okay, so suppose this is my vicinal diol and I want to protect it. So I have to form a acetal or ketal. So to bring out this change, we have three reagents. We can use a ketone with catalytic amount of H plus ions. We can use this particular ether with catalytic amount of H plus ions. We can use the Enol ether. Okay, so this is basically a Enol form of ether, and we can use this reagent as well to protect diol into this acetal or ketal version. So use any one of them and you will be able to convert this following transformation. Now this is a protected version. Suppose I want to deprotect it and want to get back my vicinal diol. So what is the method available? So you have to use a strong acidic media in presence of water. So this is about deprotection. So now you know that if you want to protect your diol into acetal or ketal version, you can use any one of these available reagents. So that will be a protection. And to deprotect, you have to use the strong acidic media in presence of water, and you will be able to get back your diol. So now let's look at the mechanism for each and every reagent. We will also see the mechanism for deprotection. Okay, so let's talk about the first method. So this is my diol and I'm reacting it with acetone in catalytic amount of H plus ions, and I am able to get the protected version. So now let's try to write the mechanism for this reaction. So I have acetone, I have H plus ions. So at first step, this oxygen lone pair of ketone will grab this proton and you have formed this particular intermediate. Then in next step, the oxygen of diol will attack at this carbonyl center, and this carbon C double bond O will break. So now we have OH. So this is now converted into single bond OH, and now this carbon is also bonded with oxygen, which is bonded with hydrogen and attached to CH2CH2OH. Now this oxygen have 3 bonds, so it will get positive charge. So basically we converted this double bond into a single bond, and we connected this carbon with this diol through this oxygen. Now in next step, the intramolecular hydrogen transfer will take place, and this bond will collapse on oxygen. So you will get, basically now you have converted your OH into OH2 plus. Rest will remain the same. So now this OH2 plus is a good leaving group. So this oxygen lone pair will attack at this carbon. This water molecule is going to leave, and you have formed O, CH2CH2O. This O is now bonded with this carbon, and this oxygen has also hydrogen with positive charge. So we just removed water, and water can act as an acid and base. So this water is acting as a base here, will grab this proton, will neutralize oxygen, and this is how you have formed the main product. So it was pretty simple, right? So you are able to convert your diol into protected version by using ketone with catalytic amount of H plus ions, and this is the mechanism for that. Okay, now let's talk about the second method available. So you have a diol, you can protect it by using Me2COMe2 with catalytic amount of H plus, and you will get this product. So what is the proper structure of this reagent? That is nothing but we have a OMe and a OMe. We have H plus ions in the reaction. So this oxygen lone pairs will grab this proton, and we have OMe bonded with hydrogen and bearing positive charge. This is another OMe. Now this is a good leaving group simply because it has converted into positive form. So this oxygen lone pair will form a double bond here, and this leaving group is now going to leave as a neutral species, that is a methanol, CH3OH. And here we will have this carbon is doubly bonded with oxygen, which is attached to another methyl group, and now this oxygen will have a positive charge. Now at this point the diol is going to come. So this oxygen lone pairs will attack at this carbonyl, will neutralize this oxygen, and we will form OMe, O bonded with hydrogen, and this is OH. So you made this double bond into single bond, you converted it, and you connected this carbon with this oxygen. So now you have this. Once again, intramolecular hydrogen transfer will take place. This oxygen is going to neutralize. Now I have O methyl hydrogen with positive charge, O CH2CH2OH. So now this time this molecule has converted into positively charged species. So now after this oxygen lone pair will attack at this carbon, this can leave as a neutral group, that is a methanol, and you have generated O CH2CH2O, and this oxygen is having one hydrogen. So this oxygen will have a positive charge. So we just removed methanol that can come that can take away this proton, neutralizing oxygen, and this is how you can get the final product, that is your protected diol. So this is the mechanism for the second reagent which you can use to convert your diol into protected form. Okay, now let's talk about the third method. So this is my diol. I can react this with the enolic ether in catalytic amount of H plus ion, and I will be able to generate the protected product. So feel free to pause the video and try this mechanism by yourself. Okay, so let's begin. So this is my enolic ether in presence of H plus ions. This oxygen lone pairs will form a double bond here. This double bond will grab this proton, and now I have generated the reactive intermediate. In next step, diol will come. This oxygen lone pairs will attack at this carbon, neutralizing oxygen. So we will have OMe, oxygen, CH2CH2OH, and this is a cationic species. Now intramolecular hydrogen transfer will take place, neutralizing oxygen will give me OMeH plus oxygen CH2CH2OH. Now this can leave as a good leaving group in a neutral form. So this oxygen lone pair will attack here. Methanol is going to leave, and we have OCH2CH2O. This oxygen is having one hydrogen, total of 3 bonds giving positive charge. Methanol will come. You can use water also here because we are anyways using a very weak acidic media. So water will be present there. Water can also do this job to grab this proton and neutralize oxygen, which will eventually give me the final product, the protected diol. So this is the third reagent which you can use to protect your diol, and this is the mechanism for it. So till now we talked about the protection methods. Let's talk about the deprotection. I want to convert my protected diol back to diol. So which reagent should I use? I'm going to use a strong acidic condition in presence of water. Okay. So what is the mechanism? So this is my diol. It's going to take this H plus ions through oxygen. So this oxygen is now bonded to hydrogen, total of 3 bonds, so it will get positive charge. Now this oxygen lone pair will intramolecularly form a double bond here, and this bond is going to break, neutralizing oxygen. So this will generate C double bond O, CH2CH2OH. This oxygen will get positive charge. Now we also have a water in the system. So this time water will come. This oxygen lone pair will now attack at this carbon. This double bond will break into oxygen, and we have O H positive. So basically I connected this carbon with water, and here we have OCH2CH2OH. Now intramolecular hydrogen transfer once again will take place, neutralizing oxygen will give me OH, O, H, CH2, CH2, OH. Here we have positive charge now. So this is a good leaving group now. So this HO bond will cleave, will form a double bond here, and this whole group is going to leave. And you have generated the product. That is, you have formed a diol and an acetone. So this is the mechanism for deprotection of your acetal ketal into diol under acidic media. So just to recall, this oxygen lone pair will grab this proton, will convert into positive form. Then the next oxygen will form a double bond here, will cleave this bond. So now we have generated this carbonyl type of moiety. So water will come, will attack here, neutralizing oxygen. Once again, intramolecular hydrogen transfer. And you have this. And this step is very important. So this single bond will break, will form a double bond here, and this whole group is going to leave as a diol. And this is my acetone. So this was the mechanism for deprotection of diol. Okay, so we have a geminal diol, right, where two OH groups are present at the same carbon. And we generally do not protect this kind of geminal diols. We have a vicinal diol, that is a 1,2 diol. This can be written like this one. We also have 1,3 diol. That can be written like this one. So this is 1, 2, this is 1, 2, 3. Now I want you to know that to protect 1,2 diol, they have to have in a cis conformation. That is, these two OH should be in the same direction. Then only you can protect 1,2 diol. You can also protect 1,3 diol in the similar fashion, and they can be protected. It doesn't matter whether they are cis or trans. In both the conditions, they can be protected. So I want you to know this, that you do not protect geminal diol. For vicinal diol, 1,2 fashion, they have to have in a cis fashion, and 1,3 diol can be protected in cis as well as trans condition. Before we jump into next slide, I also want you to know the chair conformation of cyclohexane. So 2D structure of cyclohexane looks like this. But the 3D structure of cyclohexane is something like this. Okay, so this is a 3D structure of cyclohexane. We have two types of bond. We have axial and equatorial bond. So this is my axial bond and this is my equatorial bond. This is axial, this is equatorial. This is my axial, this is my equatorial, right? This is axial, this is equatorial, this is axial, equatorial, axial, equatorial, axial, equatorial. So let me name them A, E, axial, equatorial, axial, equatorial, axial, equatorial. So here A represents axial and E represents equatorial. Okay. So now you know that this bond, what are the different bonds represent? Which bond represent axial and which bond represent equatorial? I also want you to know, okay, that in a chair conformation of cyclohexane, generally to avoid hindrance, the more stable conformation will be equatorial one. And why is that? Because when you keep the bond at axial position, we have two hydrogens in the axial position and they can do 1,3 diaxial interaction. which leads to hindrance. So that's why the more stable conformation is generally the equatorial one. So this is about the chair conformation of cyclohexane. Now you know that this is my axial bond, this is equatorial, axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial. And we generally keep bonds at equatorial position to avoid this 1,3 diaxial hindrance. So now let's move forward. Okay, so remember 1,2 diol can only be protected when they are in cis fashion, and 1,3 diol can be protected in both cis and trans. So I'm giving you some questions. For example, I have this particular diol. Will I be able to protect this diol? Well, this is a 1,2 diol. I want both OH group at cis fashion. Well, they are in a cis fashion. This bond is axial, this bond is equatorial, and they both facing downwards. So we can protect this diol. Let me give you another example. Okay, this is a second molecule. Will I be able to protect this diol? So this is an equatorial bond and this is an equatorial bond, but these two are in a trans fashion. They are like this, right? So they are not facing in the same direction, so we cannot protect this diol. What about this one? Here I have an axial bond and here I have an axial bond. Well, I cannot protect this two simply because this OH is facing downwards and this is upwards. So they are not cis. So I won't be able to protect this 1,2 diol. What about this one? Basically, I am discussing all the possible variations you can get. So this is axial, this is equatorial. Will I be able to protect it? Yes, I can, because this OH and this OH are facing upwards. So we can protect this diol. What about this one? So this is my axial bond, this is my equatorial bond. They both are facing downwards. We can protect it. What about this one? Okay, clearly this is facing upwards, this is facing downwards. This is my equatorial bond, this is also equatorial bond, but they are facing opposite, so I cannot protect it because I need a cis conformation to protect 1,2 diol. What about this one? So this is facing downwards and this is facing upward, right? You have to imagine, okay? Let me draw axial bond. Now this hydrogen is upward, this OH is downward. This hydrogen is downward, this OH is upward. So these two OH are facing opposite to each other. So we will not be able to protect this particular diol. So whenever you get confused, just draw the hydrogens and you will be able to figure it out. Another possibility can be so this is facing downward, this is facing upward, so we cannot protect this diol. So that's why I was discussing the cyclohexane conformation, because you may get a question like this. Suppose you are given a question where you have this starting material and they are telling you to protect it. Well, you cannot protect it because these two OH, this 1,2 position OH groups cannot be protected simply because they are facing opposite to each other. But if they were 1 3, so it doesn't matter if they are trans or they are cis, they are facing in the same direction or opposite, it doesn't matter that time, because 1 3 diol can be protected under cis and trans condition. Okay, let's solve one question. So if I'm doing protection, first thing I have to ask myself, will this OH, are these OH in the same direction? Well, they are. This is below the plane and this is below the plane. So I can protect this diol. So the reagent I can use is acetone under acidic media, or I can use this particular reagent with catalytic amount of H+, or I can use the enolic ether to protect these two OH groups. So what is the protected product is going to look like? So this is my oxygen and this is my oxygen, and they are protected now. Fine. So I'm giving you two questions. I want you to pause the video and try that reaction by yourself. So the first question is, the starting material is same. Here I have OH. This wavy bond represents that this is not above the plane or below the plane. Okay? You can consider it by yourself. You can take it as above the plane or below the plane. So this is my starting material. In first reaction, I am reacting this with acetone under acidic condition H2SO4. So what product I am going to get? And second condition is I am using an enolic ether in presence of this particular acid. Well, let me give you the product, and I want you to try the mechanism for these two particular reaction. The product for the first reaction is so this is the product for the first reaction, acetone under H2SO4. OH, 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 O, CH2, O, and this is the product. So pause the video and react this molecule with acetone H2SO4 to get this product, and with enolic ether under acidic condition to get this product. Try out the mechanism. So now let's solve it. Okay, so let me quickly write the reaction. Okay, and I'm reacting this with acetone with H2SO4, that will give me H plus ion, and the product we are getting is OH above the plane, oxygen, oxygen, and this is protected now. Okay, so I can write this as O Okay, so what is happening in first step is this bond is going to break. This will form a double bond here, and this bond will break. Okay, so this OH bond is breaking, forming a double bond here, and this CO bond is breaking, and you will get, so this O minus is getting this H plus, so it will be converted into OH. OH, CH2OH, rest thing will be same. OH, OH, and here we have generated a carbonyl carbon. Okay, so what I did, I broke this bond, formed a double bond here, and broke this CO bond, and this is my intermediate. Well, in product I can see a 5-membered ring, 1 2 3 4 5. So I have to cyclize in such a way that I'm going to get a 5-membered ring. This oxygen lone pair can attack at this carbon, opening this CO bond, and this will give me 5-membered ring, 1 2 3 4 and a 5. So this is my 5-membered ring. So this is my let me number them. So this oxygen is 1, then we have 2 3 4 and 5. At 2 we have CHOH, CH2OH, CHOH, CH2OH. At 3 we have OH facing upwards, so here OH is upward. We have at 4th OH facing down, OH facing down, and we have a OH group at this position, right? Now you have acetone under acidic media, you have acetone under acidic media, you have a diol. Simply protect this, and the product will be here OH above the plane, OH below the plane, and this OH can be above or below the plane. So this is the mechanism for this particular reaction. This reaction is very important in terms of the competitive exams, so take a note. Okay, let me write my second question. This question is pretty straightforward. When we are reacting this molecule with a enolic ether in presence of H plus ion source, we are getting OH, OH. So these are untouched. You cannot protect these two OH. They are anti to each other. We have already seen that. CH2O and these two oxygens are protected. So what is the mechanism? Well, mechanism we know, right? That two OH groups in presence of enolic ether forms acetal or ketal. This is the example of 1,3-diol system protection. But why 1,3-diol protection? Well, the configuration of this OH is not given, so we have to ignore it. These two OH cannot be protected because they are trans to each other, right? These two OH cannot be protected because they are again trans to each other. And these two OH are at 1,3 position, 1, 2 and 3. And 1,3-diol can be protected in cis and trans fashion. So let's go ahead and just simply protect it. And guess what? This is the product. The product we are looking for. Okay. So this is below the plane. This is above the plane. We cannot protect it. This is below. This is above. We cannot protect it. CH2O. 1, 2, 3. 1, 3 OH groups can be protected, and we are going to protect these two. So this is the mechanism. More importantly, this is actually the example of 1,3-diol protection. Okay, I have couple of more questions. So this is my another question. OH. Here we have OH above the plane, and we have also a methyl group below the plane. Here we have OH group above the plane, and here we have a methyl group. Okay, so I'm reacting this with acetone in presence of PTSA, that is a source of H plus ions, with catalytic amount of copper sulfate. So what is the product? But before you start solving it, I want you to know that the formation of 5-membered ring will favored when you have a 3-degree alcohol. So you know what is 3-degree alcohol. I have discussed this 3-degree alcohol in detail in my previous video of protection and deprotection of alcohol functional group. Here we are talking about diols. So you need to know this. The 5-membered ring formation will take place when we have a 3-degree alcohol. So when I have this acetone, it can form a 6-membered ring protection. Let me draw it. 2 products are possible. I want you to know which is the major product. So one of the product can be, so these two O can be protected. This is 1, 2, 3. 1,3-diol system, doesn't matter cis or trans. This can be formed. Another product can be, so these two 1, 2 diols. Here we have 1, 2, and they are in cis fashion. This OH is above the plane, this OH is above the plane. So this can also form, giving me this kind of product, TRO OH above the plane. So basically I'm protecting these two OH. O above the plane, O above the plane, and protect it. So which one is the major product? Well, you will be able to find out if you know this, that 5-membered ring will favor if you have a 3-degree alcohol, and this is my 3-degree alcohol. Correct? This OH is attached to a carbon which has no hydrogen attached to it. So this center is a 3-degree alcohol center, and 5-membered ring will favor, and this is the major product. Correct? And this is a OTR, O-treatyl protection. This is also I have discussed in protection on deprotection of alcohols. So this is the major product, if you know this. Let's move forward. Okay, so this is the another question. Let me see. Okay, so you have this time the HO, CH2, CH2, OH above the plane, OH below the plane, once again OH below the plane. Here we have OH and here we have OH above the plane. So this is my starting material. I am reacting this with 2 equivalents of OMe, OMe under acidic condition. So what is the product? Well, I have only two equivalents. So only two protection I can do with two diol. Correct? I can protect this. Let me number them. This is A, this to OHA, this to OHB, and this to OHC. And the product is going to be, so we have this, okay, so it can form A plus B, these two can protect. It can form A plus C, it can form B plus C. We have only two equivalents, so only two OH I have to protect. So if I do A plus B, the product will be, so this O and this O I'm protecting. Okay. I'm not touching this one. I'm not touching the C part. I'm only touching A and B part. And this O can be protected. Both are below the plane, so no problem. So this is one of the product. Similarly, B plus C can react and can give me this one. OH above the plane. Here we have once again O below the plane, protected, and we are protecting C also. So this is when B and C react. And what is the A plus C product can be? We are protecting A and C. So it will look like O above the plane, O protected. I am not touching the B part, and I am going to touch the C part. This is the next product. So only one product is going to form, either A plus B, A plus C, or B plus C. What do you think? Which one is going to be the main product? So the main product is clearly A plus C. And why is that? Just imagine the hindrance. This is so close to this one, right? This is so close to this one. But these two diols are sitting very far from each other comfortably, no problem. Okay, so that's why this A plus C is going to be the main product, simply because of the hindrance reason. And this is the main product. I hope I'm clear. So two equivalents is given, so only two possibility you can product. You can either protect this two. So all variations I have written, and the main product is going to be A plus C, simply because the hindrance is going to be the least in this case. Okay, so here is another question for you. We have CH2OH and we have OH here. And I'm reacting this with PH C double bond O H. That is nothing but benzaldehyde with zinc chloride as a Lewis acid. So I want you to know, instead of H plus ion, you can also use Lewis acid to bring out your reaction. Simply this zinc is going to chelate with this oxygen, and this oxygen will attack. Rest will be the same. So here the zinc chloride is simply activating this aldehyde by chelating with oxygen, and later this oxygen will attack. Okay. Now first I have to look at my diols, whether protection is possible or not. So this is a 1,3 diol system. 1, 2, 3. So I need not to care about cis and trans. I'm going to simply protect this two OH group with this carbon, and the product will be CH2 O, and this is my another O, and I just protected it. And I have PH and H as a substituent, so it is going to be PH and H as a substituent. So this carbon is this carbon, correct? And it has this PH and H, so PH and H. Okay. I have to rewrite it in a proper way. So this is my cyclohexane. Well, this is another cyclohexane if you look closely. Cyclohexane type of moiety. So this is 1, 2, 3, 4, 5, 6. Another 6-membered ring. So this is my 1. This is my 2. This is my 3. Right? Let me draw my 6 and 5. So this is my another oxygen, and basically I'm drawing it in a chair form. Okay. You have to look it like this. You have to imagine that this carbon is my chair carbon. So this one is going to be the axial bond and this one is going to be the equatorial bond. And I told you that equatorial product will be major. So I'm going to keep my pH group at equatorial center. So this is the main product, where pH is going to be the down plane. It will face the downside. So this is the main product. And why we are not keeping pH at axial position? Simply because of 1,3 diaxial hindrance reason. So you keep your pH below the plane, that is at equatorial, and it will be a major product. Okay, so here's another question for you. So this is my OH and this is my CH2OH, and I'm reacting this with acetaldehyde in presence of HCl. So feel free to pause the video and try finding out the product of this reaction. Okay, so diol and a carbonyl system. Well, I'm going to do the protection of this diol. So this is a 1, 2, 3 diol system. They can be cis and trans, no problem. So the product is going to be O, CH2O, and just protect it. I have a methylene hydrogen. So this carbon is this carbon, and I have a methylene hydrogen. Let me write this as Me. So here I will keep my Me and H. So this carbon is this carbon. It has two substituent, Me and hydrogen, Me and hydrogen. So this is the main product. But I have to write it in a proper way to know whether Me is at axial position or at equatorial position. So I can write this properly. So this is another 6-membered ring. So O, O, and this. I have to keep methyl at equatorial, okay, and hydrogen at axial to minimize the 1,3 diaxial interaction, and Me is going to be the below the plane, equatorial, and this is the major product. So this is it, and thank you for watching. And in my next video, I'm going to discuss about the protection and deprotection of carbonyl compounds. Thank you so much.